which provided me opportunity to study my doctoral degree at SIIT Thammasat University. So the motivation behind this lecture series is to introduce recent innovation, state-of-art knowledge, and best design philosophy in the field of structural design and analysis, adopted all around the world. Nowadays, we are talking about digital twins, development of smart material, various form of structural control and isolation systems, and nevertheless, the machine learning, AI technologies. So we would like to introduce this state-of-art knowledge, which is being carried out as a research works, and also some part of design activities, problem related to design in our lecture series. So talking about my research interest and my works, I'm today going to present about structural system under seismic loading, and also I got opportunity to work on the on investigating the behavior of 3D printed structure. So here you can see on the background, there is the 3D printed structure. When you check on the research database, very few research has been carried out to investigate the structural performance. I mean the performance of 3D printed structure is a load-bearing member. So most of the research are done for investigating the material parameter, but we were the first one to carry out the structural test. I will talk slightly about this context because today's scope is about investigating the behavior of composite structure. Also, I have some experience about investigating the behavior of fiber reinforced wall panel under impact loading, and also some research for the blast loading. So here you can see ECM, earth covered magazine, and here is some TNT, and there is the numerical model as well. And also currently I'm doing research works related to machine learning. So you can find some of my research works in here you can see ResearchGate and Scopus link, so you can find more information about my research works in this. So talking about today's presentation, I actually would like to divide it into twofold. So currently, we as a structural engineer, we are facing major two challenges. The first one is we have to accelerate the construction speed. So to accelerate the construction speed, we have to adopt the composite structure. That is the first case scenario. And another challenge which we are facing is about investigating the performance of existing structure. So I will be talking about two forms, like the part A and part B. So why prefabricated structure? So the reason behind using prefabricated structure is some of the bullet I have highlighted here. Actually, talking about cast in place construction is the better construction in terms of structural integrity. But what about accelerating the speed of construction and also about optimization of the material? Nowadays, we are talking about reducing the carbon footprint, right? So we have to think about optimizing the material consumption. Also, we have to think about environmental aspect like reduction of the wastage. So if you search on the research, so I found that the cost of formwork usually incorporate around 30 to 40%. In some cases, it even goes back to 60% of the total overall cost of the construction. So if we can use the component prefabricated structural component is the permanent formwork. So the main motivation behind this research is to use the precast component as the final part of the structural system. So here we can see some of the images. Whenever we talk about composite structure, the first image which comes in our mind is about these forms of composite structure. Either it can be CFST sections or other sections. So currently, I'm not going to discuss much about this kind of section. The section which I'm going to discuss is about precast plate encased composite section. So here you can see two forms of section. So the first one is HPCC1 and second one is HPCC2, referring to hollow precast composite column. So the advantage of using this kind of system is, think about the pier of 700 by 700 or higher than that. You have to transfer that size of column to the site. So it's very troublesome, right? It's very difficult to carry the weak section. So use this kind of system, then it's easier for transportation and also lifting. So here you can see two forms of structural system, a hollow precast composite column. So the first one, it comprises of some reinforcement which penetrate the inner core, right? You can see there are some reinforcement in the precast plate in both of the column section, and some reinforcement penetrate the inner core in case of the first one. But talking about the second one, there is no reinforcement in the penetrating the column core. So I would like to request all of you to think about it. The cross section is same, right? Only the difference is reinforcement detailing. Displacement relationship in terms of ductility, please think about it, having the same cross section but different reinforcement layout. Basically, this type of composite structures behave by three mechanisms. The first one is by cohesion. There is always the presence of cohesion between the interface. Second one is friction due to the roughness of the surface. And third one is dowel action. So talking about these three things here, if we again go to the two composite column, the dowel action one is present in the first one only for HPCC1. You can see some reinforcement penetrate, right? So from the precast to inner core, so there is the presence of dowel action, but here we don't have dowel action. So in order to improve the behavior, enhance the performance of such type of composite structure, we need to improve the interface strength. So the major criteria is having the old and new concrete, right? The old concrete, precast concrete, and new concrete, cast in place concrete. So we have to improve the interface strength. And another major change is if we try to decrease the thickness, right? So here we use the new term hollowness ratio. So here they have provided 62% hollowness ratio. Here they have provided 51% hollowness ratio. So having the smaller thickness of the precast encasement is always better. But what about the pressure exerted by the inner concrete, right? If you have the cast in place concrete, then that will exert some pressure. So that thickness should be able to withstand that pressure. We have to think those parameters as well. So I would leave to you, please think about it, which column might perform better. We'll discuss it in later slide. So this type of column I'm going to discuss. So the column which I am going to discuss is a L plate. So you can see two L plate, right? So here are two L plate which will be combined together and form a, actually they will be used as a permanent formwork and the part of the final structural system. The research gap behind this is when we talk about the previous column, right? It is box shape. It's still troublesome and space occupying, but talking about this kind of column, right, this kind of precast encasement is easier for the transportation and is very less the storage and for transportation is easier for this kind of L plate, right? And again, the main motivation behind this is to reduce the formwork requirement, right? So if we use L plate, then it serves the permanent formwork and it's very easier for transportation and storage. And again, the major concern is to use the thin precast plate, so which will increase the hollowness ratio. So in existing literature research database, when we see research database, they usually use around 50%, 40% hollowness ratio. By considering 50 mm thickness, right, the hollowness ratio increased up to 76%. So it's better. But what about the interface strength? So there is the problem, right? You have interface between two plate in here, and also the interface problem between the L plate and inner encasement, right, inner cast in place concrete. So we have to think about those parameters while dealing with such form of composite structure. So this is the composite column which I will be discussing in detail in upcoming slide. And another form of composite structure is about wide beam column joint. Generally, we provide the depth of the beam greater than the width, right? So due to the flexible requirement, obviously. So usually the width of the column is higher than width of the beam. That is the deep beam column joint. But for the wide beam column joint, right? I will again talk about deep beam column joint. So all of the reinforcement of the beam, right, they pass through the beam column joint. But in case of wide beam column joint, some of the reinforcement, right, some of the reinforcement lies outside of the beam column joint. So that is the major concern. So it will disrupt the load transfer mechanism. So that is the major concern for the wide beam column joint. So that we have to consider. So major why we use this kind of system, right? Because it has the problem, then why we are using. So these are some of the reasons. Because of architectural planning, we will have increased floor height, right? So that is the reason behind using such kinds of system, and it will enhance the speed of construction. So if we have composite structure, right, if we have monolithic, then it might not enhance the speed of construction. But if we have the composite structure, which I'll be discussing in next slide, so it will enhance the speed of construction, also decrease the overall cost, and reduce the environment impact, and due to less wastage of material. So how does this type of system work? So basically, under the event of seismic hazard or seismic event, the load, the moment exerted on the beam tries to transfer to the beam column joint and underlying foundation by three mechanisms. The first mechanism is by the direct transferring the load directly. So this occurs by the reinforcement which actually penetrate the beam column joint. Another mechanism is by the formation of strut and tie mechanism, and the third one is which cannot pass actually. So it remains as an unbalanced moment, and it results in torsion. That is the worst part. That is the most disadvantage of this type of system. So most of the codal provision, they restrict providing the width to be. I'll be talking that in upcoming slide also. They restrict to be 3 times. So width of the beam should not be higher than 3 times the width of the column. They restrict those provisions as well because of this phenomena. And in the upcoming slide, I will also be discussing about spandrel beam. Please be noted about this. So spandrel beam is a beam, you can see, right, it's in transverse direction. So this beam I will be discussing, so please take an image of this in your mind. So the research gap, if we talk about research gap for the current research work, most of the joint are tested for monolithic. So most of the wide beam joint which were tested by previous researchers comprises of monolithic. And like I already mentioned, right, to improve the performance of wide beam columns, and we need to provide spandrel reinforcement. So the early researcher in 2007, he actually tested for composite, but he did not provide it. They did not provide it spandrel reinforcement. They only provided tensioning in longitudinal direction, in plane direction, but transverse direction they did not provide tensioning. But talking about the current research, right? So the composite precast wide U-beam column joint, which I actually tested for lateral cyclic behavior, it comprises of spandrel reinforcement. It comprises of in-plane longitudinal major axis post tensioning and also transverse post tensioning. So this is the major research gap as compared to the previous research. So like I already mentioned, it is a composite wide U-beam column joint. You can think of 2 U-beam, precast U-beam and also precast column. And the joint region is always provided with cast in place concrete because of structural integrity, right? So we do not provide dry joint. We always provide wet joint in this beam column joint region. So this is the composite wide beam column joint. So this is very less research work has been carried out. So this is the research gap. Another research gap is, like I already mentioned, most of the code provision restrict the width of the beam. They actually mention that it should be, the width of the beam should be less than, or maximum it can go to equal to 3 times the width of the column. But that is not always the case, right? We cannot always do the same, right? So the research needs to be done apart from the codal provision, right? So for our tested beam column joint, the width of the beam is actually greater than 3 times the width of the column. So that is another research gap. And talking about assessing behavior of this form of structure. So there are some provision, right? Some equation, some predictive equation in the codal provision. They actually provide some guideline to estimate, to estimate the capacity, flexural capacity, shear capacity of various joint, column, and other members, right? But it's very complicated. It's very difficult to account for the complexity in configuration. I'll be talking about the complexity of configuration of such type of structure, rebar detailing, possible interface slip. There is the possibility of slip between the precast and inner core concrete, and also confinement, so delamination problem and premature buckling problem. So there are a lot of problems which the codal provision cannot account for. So the best approach is always to carry out the experimental works. So we need to carry out the experimental works, full-scale experimental works, but again, it requires a lot of resources in terms of laboratory resources, in terms of financial resources, and it might not be suitable. It might not be suitable for various scenarios. So there is a provision of numerical simulation, which we can actually adopt to investigate the behavior of this form of composite structure. So I actually use the tool LSDyna. I'm not sure you are all aware of that numerical tool or not. Actually, that tool was developed for investigating the performance of structure under extreme loading, such as blast loading, impact loading.
Which I use that in my PhD as well.
Okay, so that LSDyna is actually developed for assessing the performance of structure under extreme loading, blast loading, impact loading, which actually has high strain rate. But talking about our case, right, so lateral cyclic loading and other vertical compression or flexural bending, this type of loading are actually low strain rate problem. So we have to adopt this type of numerical to investigate the behavior of various strain rate problem. So I will be showing one video. So it actually talks about development of. I'm not sure I can play the video or not. Professor Hallquist. Please pardon me. I'm not.
Let's show the video and explain your sound. Yes.
Okay, let's move on. So let's move on to next slide. So sorry for that. You can actually watch that video in online as well. So I use the numerical tool LSDyna, like I already mentioned, right? So it has actually, beginning in the early stage, it was developed for studying the behavior of structure under extreme loading, like I already mentioned, high strain rate problem. But due to the advancement of technology, it can actually nowadays be used for assessing the performance of structure under low strain rate. I mean, quasi-static loading, lateral cyclic loading, due to the provision of implicit solver. I'm not sure you are aware of that or not. We have actually implicit solver and explicit solver. So due to the provision of implicit solver, we can actually solve the problem. There are some convergence issues for sure, but we can actually solve the problem. So before carrying out the numerical study of the proposed L-shaped precast plate and wide beam column joint, I actually carried out methodology verification, because the modeling tool which we use, right, that needs to be verified. So for that, let me slightly explain about methodology of study. So the methodology verification was first carried out initially using the HPCC column, which I previously mentioned, hollow precast composite column, two forms of HPCC1 and HPCC2. Later on, same methodology was adopted to investigate the behavior of L-shaped precast plate encased composite column, followed by studying the behavior of seismic behavior of full-scale interior and exterior wide U-beam column joint, followed by studying the behavior of half scale. And again, I already mentioned, right, so it's very difficult for carrying out the experimental works for the full scale test specimen. So the experimental works was carried out for reduced scale, 1:2 reduced scale, half scale interior wide U-beam column joint. For the control and modified, I'll be discussing it in upcoming slide. So at first, let's start from methodology verification. So I believe this content, this methodology, this slide which I am referring, it might be helpful for some of the students who are actually going to do research works for their master's and their doctoral study. Please, you can adopt some of the methodologies mentioned herein. So this is the methodology of my study. So at first, a selection of the modeling parameter. So in the numerical tool, right, it's detailed finite element, right? This is so we have to think about mesh sensitivity analysis. We have to think about boundary problem. We have to think about solver. We have to think about material model, concrete material model, rebar material model. We have to think about interface problem, delamination problem, premature buckling problem. So we have to think a lot. So methodology verification was carried out for these two forms of column. The first one is corresponding monolithic column. Actually, it was not tested by me. It was tested by the previous researcher, Kim et al. 2016. It was verified numerically by me. So this is the monolithic column corresponding HPCC1 and HPCC2. So these are three forms of column which were simulated in order to assess the in order to actually verify the modeling methodology and also investigate the suitable material model. We have actually various forms of material model in that numerical tool: continuous surface cap model, MAT 159, shear Murray cap model, MAT 145, KNC material model, MAT 079, 073, sorry, Winfield material model 084. So we have tremendous library of concrete material model and rebar material model. Also, we have library of contact algorithm in order to capture the interface strength between the old and new concrete. So this is the numerical model for monolithic and composite column, which was tested for axial load followed by lateral cyclic displacement. This is the test setup used by the researcher. Similar boundary condition was used in the numerical simulation, and the load was applied similarly in the same fashion as the test setup. So 7% of axial load was applied from the top of the column, followed by 3 cycles of drift. So this is the way the test was carried out, and in the similar way numerical simulation was carried out. From the numerical simulation, it was observed that, so at first investigation of the consecutive concrete and rebar metal model was carried out for the monolithic column. We can see the swelling of concrete, the plastic inch length. The numerical model could capture the behavior of the test specimen in terms of load displacement behavior, in terms of cracking. So by this way we can use the selected material model, right? So the concrete material model which was adopted to simulate, we can use for the other purpose as well. So this is the methodology verification for the monolithic. And talking about composite column, right? So for the composite column, we have to think about contact algorithm. There is the interface problem. So the numerical model actually can capture the behavior of composite column. So here you can see the buckling, right? And also delamination of encasement from the core. So this is the result from HPCC1, and this is the result from HPCC2. I have not explained all of the result in detail in here. Please refer to the publication. So the contact algorithm, interface contact algorithm works in a manner like, I think we all are aware of PM interaction surface, right? Any value of P and M within the surface, the structure is safe, and any value outside the surface, the structure is not safe, right? We can think about a column. So here also it creates an ellipse. You can see a equation, right? It creates an ellipse. So within any value of normal and shear stress, within that boundary, there is no occurrence of slip. And if the stress exceeds, then there is the occurrence of slip and finally delamination. So this is the way this tie-break contact algorithm actually works. So it can capture the behavior of composite column also. So I initially asked you all a question, right? So which column might perform better? So let me answer. So talking about HPCC1, right? HPCC1 has reinforcement which penetrate the core, right? So it actually improves the dowel action. So that is the reason the load capacity, the peak load capacity for the, as compared to these two columns, right? HPCC1, HPCC2, it is from the test result. HPCC1 performed better in terms of load displacement behavior, but in terms of ductility, so I'm not sure you still have the image of that HPCC2. It actually consists of 2 forms of hoop, inner and outer hoop, and also saddle shape of reinforcement. So ductility of that system was better. So it's from the test results. So after verifying the modeling recommendation, right, modeling methodology, the next step is to assess the performance of studied column. So this is the composite white composite precast full scale L-shaped precast plate in case control and modified column. So investigation of seismic performance was carried out. Here you can see in the image, right? So this is one L plate, and followed by this is another L plate. So these two L plate are combined together, and still the main motive for using these forms of L plate is to use it as a formwork. So it is not actually the structural member, but our concept is to adopt it as a permanent formwork for the structure, right? And also it will have the composite action like inner and outer concrete, right? Wet and dry concrete will have the composite action. That was our main motivation. The main structural element is still the cast in place concrete, right? We can see heavy reinforcement in the inner core. So this is 2 L plate which will be combined together to form the final form of composite structure. So these are some of the detail of the column which are actually used in the site. So these are some of the images and some of the sectional property. And like I already mentioned, there is the problem of interface strength, right? So there is no any medium to transfer the load, right, from the precast to inner core, right. Only there is the provision of cohesion and friction. So what we want to use dowel action as well. So this is the first modification, MC1, by addition of U-hook bar. Second modification by using some shear strut. And third modification, we try to improve the confinement, like making it fully precast in case, right, box shape of column. So this is another modification. And the fourth one is by using this form of steel shape blade. So it is the fourth modification. Actually, the various parametric study was carried out. I have just highlighted 4 of them. And talking about the simulation result of the control composite column, here we can see there is the buckling of there is buckling and delamination, right, precast encasement. So that is the major reason of failure. Even though the column exhibited ductile behavior, talking about the New Zealand standard, right, it actually mentions having 3 to 6 value of ductility, right, is ductile structure. So it performs it has ductile behavior, right. But the problem is about the failure by delamination of the precast. So we want to improve this behavior. So the numerical simulation was carried out for various modification, control and modification. So from the numerical simulation, as you can see, the fourth modification with the use of steel shape blade perform the best one in terms of load displacement behavior, in terms of drift capacity, in terms of ductility. So the advantage of using this approach, right, so we don't need to test for MC1, MC2, MC3, because again, carrying out experimental works is very tedious job. So we can only carry out the experimental works for control and MC4. That is the good choice, right? So just carry out experimental and just actually we have to verify it by experimental means as well. We cannot just rely on the numerical simulation, but we can take it as a proper estimation if the modeling approach is correct. So these are the results which I have shown. I'm not talking about test result for this type of composite column. So I'm just talking about simulation result. So these are the results which I have already discussed about composite column. Now I'm going to talk about composite wide beam column joint. So this is a unique type of joint. Actually, you can see here, like I already mentioned, the joint region is always in place. And this is the actual constructed structure. So these are some of the investigated interior and exterior joint. Here we can see 2 precast U-plate and having precast column as well, and the joint region is always cast in place. So these are the investigated exterior and interior joint. Here I would like to highlight that the size, the length, right, the span of the beam in either side of the this joint, right, is not the same actually, because the joint was extracted from the real building, right? So it's actually not the same. So it will also affect the behavior, having the different span. So that I will also be talking in the upcoming slide, but I just want you to highlight that part as well. The span in either side of the joint is not same for the beam. So here you can see 21O and 36O. So these are investigated exterior and interior joint, and this is the construction procedure. So we have a U-shaped precast U-beam having embedded a truss. So this is a special type of reinforcement. Like I already mentioned before, right, it's very difficult to assess the behavior of this form of composite structure by the means of some standard, ACI standard or some other standard, right? It's complexity in reinforcement. These are A truss, 5 rows of A truss I would like to highlight again. So we have 5 rows of A truss, post-tensioning, and this is the layout, parabolic profile of post-tensioning. And this is the final structure. Here you can see, right, the width of the column and width of the beam, right? Width of the beam is higher than width of the column. So this is the composite wide beam column joint. So I again here highlighted here, we have 5 rows of A truss, because later on we'll be carrying out optimization study. So I just try to highlight it here. So these are some of the additional details. I'm not going to talk more about it. We actually connect the 2 precast column by the means of mechanical splices. So this is the simulation result. So let me show a video. So this is a video from the numerical tool LS-DYNA. The damage fringes are shown in terms of effective plastic strain, having 1 full damage, 0 no damage. So there is initiation of transverse crack. You can see the transverse crack, followed by diagonal shear crack, and finally cross-diagonal crack. So the joint is simulated under axial load followed by lateral cyclic loading. So you can see the formation of cross-diagonal crack, right? And ultimately failure of the specimen occurred due to crossing of concrete under a wide beam near column face. This is the video from the numerical tool. So here you can see a degradation of the strength, right? It's sudden degradation of the strength, which is not desirable actually. So the reason behind is due to the formation of torsion crack. The modification of the improvement of the performance of this type of joint needs to be carried out, right? So before that, we need to we actually carried out optimization study to so the improvement of this type of the improvement of behavior, seismic behavior of this type of joint, we need to add some of the reinforcement in some direction, right? So before doing that job, we actually try to optimize if we can optimize any other rebar configuration. So for that, we actually remodel it with 5 rows of ATROS, 4 rows of ATROS, and 3 rows of ATROS. From the numerical simulation, as you can see, the strain, right? Strain in reinforcement in 5 rows and 4 rows is similar. 3 rows is too much. There is yielding of reinforcement. And talking about interface strength, so 4 rows and 5 rows almost the same. Talking about low displacement behavior, 4 rows and 5 rows almost the same. So the optimized row, it can be used 4 rows instead of 5 rows. So the reinforcement which we save, right, from decreasing the number of arrows was used as a spandrel reinforcement. So added reinforcement was spandrel reinforcement. So here we can see, like I already mentioned before, right, actually the load transfer carries out by 3 mechanisms. The first one is the direct mechanism, second one is strut-and-tie mechanism, and third one is by it cannot pass actually, it actually remains as an unbalanced moment. So we have to decrease that portion. So in order to decrease that portion, the first modification is done by providing the spandrel reinforcement, like I mentioned, in the transverse direction spandrel reinforcement. So it will improve the load transfer path. The first modification. Second modification, by confining. Initially, we believed that providing post tension in plane direction only will perform the joint will perform better, right? Because we are just testing in one plane, right? But later, seeing the results from the numerical simulation, we felt like if we try to confine the joint in the transverse direction as well, then it might perform better. So second modification was by confining, by providing transverse pre-stressed tendon. Third modification, by providing both spandrel reinforcement and pre-stressed tendon. So these are some of the numerical parametric study which were carried out, and these are the results from the simulation. From the numerical simulation, we can see that modified full-scale joint 3, that means provision of spandrel reinforcement and transverse confining, perform the best one in terms of low displacement behavior, in terms of cracking, initiation and formation of cracking, and in terms of ductility. So it perform. Here you can see, if you remember, the 3 is the limiting criteria, right? So all of the joint, they exhibit limited ductility, but modified full-scale joint 3, it exhibited ductile behavior. So actually, like I already mentioned before also, we actually will test for the 2 joint only. The first one will be the contour and second one will be the MFSJ3, modified full-scale joint 3. So these 2 joint will be tested, and I will be talking about this test result in upcoming slide. So these are some more simulation result in terms of principal stress, load transfer path. Here we can see in the third one, right, last one, modified full-scale joint 3, the formation of strut-and-tie mechanism, right? You can see the zone 2 is the width is increased, right? So this type of joint behaves well by the provision of spandrel reinforcement. Actually, if we compare about B and C, right, B performs better. So provision of spandrel reinforcement perform better. Also, modified full-scale joint 3 perform the best one. The confining, transverse confining also helps. And also here we can see at the same drift, right, we have to compare always at the same drift. At 4% drift, if we compare in terms of effective plastic strain, again, 1 full damage, 0 miss, no damage. So here we can see at 4% drift, damage level in modified full-scale is very less as compared to other. So it performed the best one. So in the upcoming slide, I will be discussing about experimental works, half-scale experimental works, which were carried out for control and the third one. So this is the test setup actually. So I will be going to next slide. The investigation of seismic performance for half-scale interior wide view beam column joint. So these are some of the test preparation. So this is splices which will be adopted to connect upper and lower precast column. This is the actuator having capacity 500 kilonewton. Like I mentioned, it's very difficult. It's very difficult to actually test for the full scale joint. So we actually reduce it to half scale. This is the actuator of 500 kilonewton capacity, which we can actually test for in-plane cyclic loading. And this is U beam, which is rooted with A truss. So we can see the A truss reinforcement. Here we can see extruded reinforcement of the column, which will be later connected by the splices, by the provision of mechanical splices. So this is the transverse section along the joint, and this is the longitudinal section along the whole beam column joint. So these are some of the additional details. And this is the provision of post tensioning. Actually, for each strand, 12.17 ton was applied as a post tensioning in plane direction. So right now I'm talking about control joint, right? So control joint only has post tensioning in plane direction. And talking about modification, the first modification was done by providing the spandrel reinforcement in the transverse direction, and actually it's closed stirrup. This is the first modification. And second modification is to provide the transverse confining ties. So it's actually just 1,000 millimeter, right? So it's small span, so it's very difficult to incorporate the parabolic form of post tensioning in this transverse direction. So instead of that, we use pre-stressing tie rod. We apply torque. So all of the values, all of the calculation comply with the full scale. So all of the calculation were reduced down to half scale based on the full scale configuration. So these are some of the modification details. And the test was carried out under in-plane lateral cyclic loading. The axial load by means of axial load was applied by pre-stressing from the column and followed by lateral cyclic load. Here you can see the loading protocols, and also you can see some of the, I'm not sure it's visible or not. I'm sorry for that. It may not be visible as well. So here are some of the data acquisition system. So some of the data acquisition system in terms of LVDT, in terms of sensors, in terms of strain gauges, which we use to extract the information of strain in reinforcement, strain in concrete. So there are several parameters which we need to carry out, which we need to consider during carrying out the experimental works. And I have the experience. I actually worked for 3 days continuously for each joint. It was a good experience for me at that time. So these are test setup, and these are some of the results from the test experimental works for the control and modified. Talking about the low displacement behavior for the control joint, right? You can see we can just test up to 5% drip. Talking about the modified, we actually could test up to 7% drip. So it actually performed far more better in terms of low displacement behavior, in terms of stiffness, in terms of ductility. So here you can see it is limited ductile, and this ductile structure, the modified joint is ductile structure. And some of the comparison here I'm showing about cracking behavior. So this type of joint, this type of wide beam column joint, they always exhibit the same fashion of cracking. So they always have flexural crack followed by shear crack followed by torsional crack. We cannot avoid that. We only can delay the initiation of the crack. Here we can see for the this is the control and this is the modified, right? So at 1.1% drift level, there was occurrence of shear crack, but in case of modified, it came around 2%. So actually, it's just delay, but by that way, it improved the performance. But there is always occurrence of the crack, right? The flexural crack, shear crack, followed by torsional crack. So in terms of cracking, right, here you can see control and modified. The number of crack in control was far more as compared to number of crack in modified. So in terms of everything, low displacement behavior, energy dissipation capacity, ductility, strain in reinforcement, the modified joint exhibited better performance as compared to the control joint. So after that, numerical simulation beam column joint for various seismicity of Thailand. So there is an approach named displacement-based approach, which was initially developed by researchers, is highlighted here. They actually propose a assessment which can be adopted for structural system in order to use it at various seismicity and various soil type. Here we can see. So actually, I use the seismicity of Thailand, right? I was doing research for a project in Thailand. So I use the seismicity of Thailand and the soil type in Thailand. Publication. So for the L-shaped precast plate and full-scale precast wide U-beam column joint, several models were suggested. So talking about Bangkok region, right, it's very soft soil. So we can actually adopt control joint. We don't need to go for modification, right? So you can think of it as a type design for various seismicity and soil type. So various joint and various composite column configuration were adopted for various seismicity and various soil condition for various seismic zone of Thailand. So this was the major contribution of my research. And talking about recommendation, right? So Thailand actually it lies in the region of low to moderate seismicity. But how about our region? Our region is very high seismicity, right? So this kind of wide beam column joint, composite column, right? So this kind of structure are usually adopted in regions of moderate seismicity, right? But talking about high seismicity, we have to consider other factors as well. So here we are already aware that we have like experienced various level of seismic scenario, right? So also the major problem is about the basin, right? So we have Kalimatic clay, right? It's very soft soil for Kathmandu basin. So we have to consider this both factor. And also in terms of seismicity, so this actually is the image from the recent research. Actually, I was a part of it as well. So this is around 2018 research by Roman. So they actually recommend 1.02 PGA. And from our research, it was recommended 0.9 PGA. But the current research only can be adopted until 0.45 and 0.37. See the difference. So it's the major task for all of us to think about how we can improve the performance of such type of joint or such type of composite structure or any other type of structure, so that they can be adopted for our region with high seismicity, right? So we have to think about this. It might be a future recommendation for some of the researchers which would like to carry out research on this area. So until now, I discussed about the behavior of composite structure. So the major motivation behind using this kind of structure is to accelerate the construction speed, right? But how about the existing structure? So we have to actually carry out the research works for the existing structure. We are already aware, right? After the Udaipur earthquake, there was the formulation of NBC standard, right? 105 and 205, and it was revised in 2012. And before the implementation, it was in the state of implementation, but there was the occurrence of Gorkha earthquake. And now we have got seismic design standard NBC 105. And all of the previously constructed structure, right, thinking about these structures, right, they have to perform, right, in order to meet the seismic demand of NBC 105, right? So we have to assess the performance of this structure. So that is the major challenge for us being as a structural engineer, right? So to carry out the research work, it's ongoing research. I'm not going to talk much more detail on this. Actually, it's ongoing research. So we actually studied for the interior and exterior joint for NBC 205 1994, NBC 205 2012, and the well-designed joint complies with the seismic demand of NBC 105. So these are some of the joint configuration. And talking about NBC 1 and NBC 2, right, the behavior is strong beam with column, right? It's not desirable. So we have to actually have the strong column and weak beam, right? So that is capacity-based design. So this joint only comply with the requirement of the standard. So NBC 3, which is the well-designed based on NBC 105. So we have to actually assess the behavior of NBC 1 and NBC 2 and propose some strengthening measures. So again, we again come from the zero, right? We have to again use the methodology verification. So numerical simulation was again carried out, and it was verified with the experimental works. You can see the experimental results in terms of load displacement in the below chart, and the numerical simulation result from LS9. Okay, so after carrying out the validation study, right, so we are ready to go to assess the performance of the structure. So we actually assess the performance of the structure and propose some of the strengthening options. So some of the tests were carried out. So some of the strengthening options are probable strengthening options, I would like to say here. CFRP, steel jacketing, reinforced concrete jacket. We did several tests to calibrate the material parameter, and the research was carried out by the member highlighted here. So it's actually ongoing work. I'm not going to talk much more detail on this topic. And another topic which I'm currently being involved is supervising master's student. Actually, they are master's student from COPA, and they are assessing the seismic risk assessment of RC building typology. They are actually using Perform 3D based and OpenC based macro modeling, and LS9 and Abacus based micro modeling, and it's actually supervised by me and Professor Manjib sir. So these are some of the ongoing research works which are being carried out. And the next research works which is currently being carried out by me is about machine learning. So I'm not also going to talk much more detail about this because it's not the scope of today's presentation as well. We actually use non-ensemble and ensemble machine learning models to assess the performance of to assess the behavior of the target. So we have some input, right, to have the targeted output, right? So I'm not going to talk more detail of this, and also cross-validation works needs to be carried out. So actually, like sir at the beginning of my introduction, he already mentioned that I was lucky enough to be involved for carrying out the research works related to 3D printing. So in the research database, right, if you take a look in the research database, there are no research work being carried out to assess the performance of 3D printed structure as a load-bearing member. There are research works which investigate the material property, but not as a load-bearing member, as a structural member. So we actually carried out tests to characterize material properties in terms of tension, compression, shear, normal and normal stress, normal interface strength, and shear interface strength. And we actually tested 3 types of wall. The first one is plain wall, and 2 wall are textured wall. This is the diamond wall, and this is the cap wall. Again, please refer to the publication for more detail. So the test was carried out, full scale testing, and also numerical simulation was carried out. We proposed the unique modeling system for characterizing the behavior of this type of joint system. And finally, we proposed the design guidelines. So various type design were created, and which is currently being implemented in Thailand. So this was the contribution. So the reason behind I'm showing this slide is the material, the numerical modeling methodology which I adopted to assess the behavior of such type of printed structure can actually be adopted to investigate the performance of masonry structure. So I believe some of you are doing research about masonry structure. So we have simplified micro modeling, right? I think all of you are aware of that. We have brick and we have interface, right? Similar to this one, we have layer and we have interface. So the modeling recommendation provided in this research can be actually adopted to investigate the performance of, we have to assess the performance of cultural heritage structure, right, on reinforced structures. So it can be adopted. So that's the reason behind I'm showing this topic in here. So that's all for my side. So I will be concluding. So this is the first lecture series. So we have many more to go. So these are some of the, I'm not going to talk more about the presenter and other things for this lecture series. So please stay with us, stay tuned. These are some of the upcoming lecture series, and these are some of the references. Thank you very much for your attention. Thanks a lot. Okay.
Hello everyone, once again. हामीले त्यो हाम्रो फेसबुक पेजबाट लाइभ पनि गरेका छौँ, त्यसैले कति साथीहरूले चाहिँ यो के भइरहेछ भन्ने पनि लागिरहेको होला. Actually, you are in the room of Structural Engineers Association CNEP's lecture series, first lecture. We welcome you to the room once again. र हाम्रो यहाँ अहिले फिजिकल अडियन्सहरू more than 40 हुनुहुन्छ र अनलाइनबाट अहिले मैले हेर्दाखेरि 17-18 जना भन्दा बढी देखिरहेको थिए. यहाँहरू सबैले पेशेन्टली यो यति ब्युटिफुल, हाइली कम्प्रिहेन्सिभ, भेरी ब्रोड लेक्चर जुन थियो यङ डाक्टर सतीश पौडेलको प्रेजेन्टेसन, त्यसलाई एटेन्सनका साथ एटेन्ड गरिदिनु भयो, त्यसको लागि धेरै धेरै धन्यवाद. र यस पछाडि हामी क्वेसन आन्सर सेसनमा जाउँ. हामीले डेलिभरेटली नै अलिकति डाक्टर साहबलाई अलिकति लामै प्रेजेन्टेसन गर्न दियौँ, बिकज इट वाज सो beautiful, so comprehensive, very detailed. So I hope our engineering students of masters as well as bachelors in civil engineering, let alone the researchers and academics of structural engineering, earthquake engineering, would benefit from this. So I open the floor for question answer session. And if you have any questions from the floor, you can raise here. And to those who are joining us via online through Facebook Live or Google Meet, you can raise your hand or just put off your question in the chat box. So the floor for question answer session opens now, and I really look forward to receiving your questions. And Dr. Satish would be kindly answering to your questions. Yes, sir.
I think we have a question.
Okay.
I saw a question. Someone asked about material of precast.
So probably. So there has already been a question probably received in one of the platforms. So Dr. Satish would be glad to answer to that. Thank you.
I saw a question which pop out. Okay, Sabin Raut, sir. So thank you very much for your question. So the material of precast panel is concrete actually. Is concrete material. So if you have other questions, please you can ask. Please. Okay. Azir. Actually, त्यो सिस्टम चाहिँ कस्तो भने चाहिँ कम्पोजिट सिस्टम हो. कम्पोजिट भनेको कस्तो भने चाहिँ दुईटा यु बीम भयो है, अनि जोइन्ट रिजनमा चाहिँ कास्टिङ प्रेस कन्क्रिट नै भयो, अनि त्यसपछि दुईटा प्रिकास्ट कोलम which will be joined with mechanical splices. हजुर दुईटा फरक नै हो. दुईटा प्रिकास्ट कोलम which will be joined with mechanical splices, just joined in the column.
Thank you. Please. Very nice presentation. Engineer, researcher, lecturer, behind the box basically. Was research very
okay.
Probably hard skill experiment you are
Azure.
And this was more validate one.
Already.
Your skill effective like considering problem. In my case, basically, if you calculate that design. हाम्रो जुन सिमेट्री गराउनु पर्ने थियो त्यो पनि कहिले राइट भएन हैन, तर कुनै सबै सिमेट्रीमा हैन, कुनै सिमेट्रीमा चाहिँ बस कम्प्लिट गर्नु पर्ने त्यो ठ्याक्क शियर फोर्सबाट ब्यालेन्स गर्नुपर्ने छ नि. त्यो चाहिँ जब अल्टिमेट सिस्टममा पुग्दासम्म पनि त्यसमा देखिरहेको कुनै एक्सपेरिमेन्ट कुनैमा देखिन, बट मेरो पार्ट अफ त्यो रिसर्च भयो बेसिकली फ्याक्टराइज कसरी गर्ने, त्यो कसरी ब्यालेन्स गर्ने नभएर आई डिडन्ट केयर मच. अब अहिले ठ्याक्कै आगो भएर आई गट दिस चान्स हैन. र त्यो छ बेसिकली अहिले यो कम्पोजिट ट्राई गर्दाखेरि पनि कम्पोजिटमा अहिले काम पनि गरिरहेको भएर यो कम्पोजिटमा नयाँ भनेको चाहिँ यो इपोक्सी बन्डिङको आइरहेको छ हैन. बेसिकली मोर देन यो सिरिज स्टक भन्दा पनि इपोक्सी बन्डिङको चाहिँ बडी रिलायबिलिटी छ भन्ने छ. तर तपाईँको जुन यो याद सेट अहिले लाग्छ नि, त्यो कोलममा राख्दा त्यो कङ्क्रिट चाहिँ हाम्रो चाहिँ कास्टमिस्टिक भएको भएर चाहिँ त्यहाँ अलिकति प्रब्लम हुन्छ किनकि जुन सियर स्टोरले गर्दाखेरि सियरलाई इफेक्टहरू आउँछ नि त्यो चाहिँ हाम्रो अथवा स्लिपेजकै कुराहरू पनि त्यो राम्रो अहिलेको हाई स्ट्रेन्थ यो इपोक्सी बोन्डिङ प्रब्लम छैन त्यसै गरी तपाईँले यसमा के गर्नुभएको छ इन्भेस्टिगेट गर्नुभएको छ यो पार्टमा चाहिँ हाउ क्यान इट बी लाइक मेक मोर रिलायबल त्यो केस त्यो कम्पेरिजन टु सियर स्टोर्स अल टाइप अफ बोन्डिङ अर्को चाहिँ यो आई डोन्ट अन्डरस्ट्यान्ड पनि है त्यो सुरुमै त्यो हलो प्रिकास्ट कन्क्रिट गरौँ भनेको चाहिँ त्यो हलो थियो कि थिएन मैले त हलो नै बुझिनँ कि सुरुमै त्यो पहिले त्यहाँ कन्क्रिट पनि देखाएको जस्तो लाग्यो अलिक क्लियर भएन कि कहाँ बसेर के मलाई होइन त्यो एसपिसिसी 1 र एसपिसिसी 2 नै मैले बुझिनँ कि यहाँ कसैबाट त्यो गर्दाखेरि त्यो कसरी त्यो काम गरेँ मैले अलिक गर्नु पाइनँ त्यसलाई क्लियर गरेँ लास्टमा यो मैले हुन त तपाईँले त्यो ब्याङ्कको रिजन त दिनुभयो होइन साइन्टिफिकको कुरा ल्याउनु भयो 2.5G सँग कुरा गर्नुभयो लास्टमा गएर एनबिसी 103 रिक्वायरमेन्ट आई थिङ्क त्यसमा पनि मिट भयो भने जस्तो लाग्यो होइन यहाँ यो कोलम दिनको जोइन्ट रिक्वायरमेन्ट बट मलाई कसरी त्यो चाहिँ ब्यालेन्स भयो लास्टमा त्यो जानु मन लागेको त्यो त्यहाँ पछि छोटो रेजोल्युसनमा
Okay, thank you very much. These are the wonderful questions. So फर्स्टमा स्केलिङको कुराबाट सुरु गरौँ अब स्केलिङको कुरा गर्दाखेरि खासमा कस्तो हुन्छ भनेपछि तपाईँको फुल स्केलबाट हाफ स्केलमा जाँदै गर्दाखेरि जस्तो हामीले पर्सेन्टेज अफ स्टिलको कुराहरू गर्छौँ है एस्पेक्ट रेसियोको कुराहरू गर्छौँ ट्रान्सफर्स रेन्फोर्समेन्टको पर्सेन्टेजको कुराहरू गर्छौँ त्यो के गरिन्छ भने चाहिँ फुल स्केलमा जति युज गरेको थियो नि त्यो रिड्युस स्केलमा त्यति नै युज गर्नुपर्ने हुन्छ कम्प्रेसिभ स्ट्रेन्थको कुराहरू होला त्यो सबै कुराहरू त्यो अनुसार गर्दाखेरि चाहिँ मेरो केसमा है पार्टिकुलरली अब हजुरको केसमा आई डोन्ट नो मेरो केसमा त्यो प्रब्लम आएको थिएन किनभने I did a comparison of low displacement behavior, ductility for the full scale and half scale. It was almost the same, minor deviation. And also in terms of cracking behavior, it was almost the same. So scaling effect was not too much encountered in my research. So I think I answered that first question. Talking about epoxy, I'm sorry to say I didn't actually did that use of epoxy resin. So it might be a good option. So I didn't do the research about that, so I'm not able to answer that part. So यो थर्ड वालामा चाहिँ यस कस्तो छ भनेपछि जस्तो मैले यसमा अलिकति थोरै हाइलाइट गर्न खोजेँ यो खासमा पुरानो रिसर्च हो कि मेटलले गर्नुभएको रिसर्च हो अब यसमा हेर्नुभयो भनेपछि अब यहाँ बाहिरतिरको यो प्रिकास्ट इन्केसमेन्ट छ नि बक्स सेप अफ इन्केसमेन्ट अब यो भनेको तपाईँको प्रिकास्टको भयो अनि भित्रतिर चाहिँ जुन यो खाली भाग देखिराख्नु भएको छ नि यो भनेको चाहिँ पछि कास्टिङ प्लेस कन्क्रिट फिलअप गर्ने पार्ट भयो अब यो कस्तो छ भनेपछि अब यो पेपरमा हेर्नुभयो भनेपछि यसको म्यानुफ्याक्चरिङ प्रोसेस अब यो धेरै सजिलो चाहिँ छैन पहिले के गरिन्छ भने प्रत्येक प्रिकास्ट प्लेटहरू छ नि एउटा प्लेट दुईटा प्लेट त्यो प्लेटलाई रोटेट गर्दै जस्तो पहिला यसरी प्रिकास्ट प्लेट राख्यो रेन्फोर्समेन्ट लेआउट गर्यो अनि यसलाई यसरी रोटेट गर्यो फेरि रेन्फोर्समेन्ट लेआउट गर्यो इट्स इज अ बिट tedious task. So this is the way they actually manufacture this composite column HPCC1. It comprises of 75 mm thickness. So अघि मैले तपाईहरुलाई एउटा कम्प्यारिजनको कुरा जस्ट सोचिराख्नु भनेको थिए जस्तो यसमा कम्प्यारिजन गर्दा having the same cross section 700 700 700 700 कुन कोलमले चाहिँ परफर्म बेटर गर्यो in terms of test result भन्ने मैले एउटा क्वेशन राखेको थिएँ अब यसमा हेर्नुभयो भनेपछि अब यो कम्पोजिट स्ट्रक्चर भन्नासाथ कस्तो हुन्छ भनेपछि तपाईको इन्टरफेस स्ट्रेन्थ ट्रान्सफर मेकानिजम भनेको चाहिँ सुरुमा कोहेसन हुन्छ कोहेसन इज अलवेज प्रेजेन्ट एन्ड फ्रिक्सन त्यो सर्फेसको रफनेसको कारणले गर्दा त्यहाँ फ्रिक्सन हुन सक्ने भयो अब त्यो कतिको रफ गराउनु भएको छ त्यसमा भर पर्ने कुरा भयो अनि फाइनली डबल एक्सन सो अब यो कोलममा हेर्नु भयो भने कम्पोजिट कोलममा चाहिँ डबल एक्सन छ जस्तो यहाँनिर तपाईको रेन्फोर्समेन्ट पेनिट्रेट गरेको छ इनर कोरमा तर यसमा हेर्नु भने रेन्फोर्समेन्ट पेनिट्रेट गरेको छैन भनेपछि यो केसमा चाहिँ तपाईको के हुन्छ भनेपछि लोड ट्रान्सफर चाहिँ राम्रोसित हुन पाएन तपाईको बाहिरदेखि भित्रसम्म त्यो कारणले गर्दाखेरि चाहिँ अब यो टेस्ट रिजल्ट हो है न्युमेरिकल सिमुलेसन पनि भेरिफाइड हो अब उनीहरूले गर्दाखेरि जस्तो कि मेटलले गर्दाखेरि चाहिँ उहाँले चाहिँ के पाउनु भयो भनेपछि जस्तो पिक लोड क्यापासिटी है जस्तो यो तपाईको लोड ट्रान्सफर भइसकेपछि त ड्यामेज त हुन सकेन नि डिलामिनेसन त हुन सकेन नि प्रिकास्ट इन्केसमेन्ट त्यही भएर पिक लोड क्यापासिटी चाहिँ HPCC1 को धेरै छ because of the provision of double action only double action को कारणले गर्दाखेरि चाहिँ लोड पिक लोड क्यापासिटी हाईएस्ट भएको छ एज कम्पेयर टु HPCC1 तर HPCC1 मा हेर्नु भयो भनेपछि एउटा त यसको प्रिकास्टको इन्केसमेन्टको थिकनेस नै धेरै छ 100 mm छ यसको 75 mm छ अब थिकनेसको कारणले गर्दा नि एडिसनल कन्फाइनमेन्ट भयो अर्को यसमा हेर्नु भयो भनेपछि डबल हुप छ कि जस्तो यसमा आउटर हुप छ एउटा अर्को चाहिँ इनर हुप छ अनि यो स्याडल टाइपको एउटा स्पेशल रेन्फोर्समेन्ट छ यो तीनटा टाइपको रेन्फोर्समेन्टको कारण अनि तपाईको त्यो कन्फाइनमेन्ट एडिसनल कन्फाइनमेन्ट ड्यू टु इन्क्रिज इन थिकनेस अफ द प्रिकास्ट प्लेट इट कन्फाइन्स well. So ductility was found to be better in terms of when we compare these two columns, ductility of HPCC2 was found better as compared to HPCC1. भनेपछि यो क्वेसन पनि मैले एन्सर गरे जस्तो लाग्छ मलाई. अनि तपाईको अर्को क्वेसन भनेको चाहिँ अब मैले दुईटा फोल्डमा यहाँ कुरा गरेको हो खासमा. एउटा भनेको चाहिँ हाम्रो रिक्वायरमेन्ट, हामीलाई च्यालेन्ज के छ भनेपछि एउटा हाम्रो कन्स्ट्रक्सन स्पिड बढाउनु पर्ने छ है. अब त्यसको लागि हामीसित अप्सन भनेको प्रिफेब्रिकेटेड स्ट्रक्चरहरू युज गरेर हो. अब अर्को अप्सन भनेको त एक्जिस्टिङ स्ट्रक्चर पनि त छ नि. एक्जिस्टिङ स्ट्रक्चर पनि त पुरानो कोड एनबिसी 205 1994 2012 बाट डिजाइन भएको स्ट्रक्चरहरूको पनि एसेसमेन्टको पार्ट. किनभने चाहिँ आई थट लाइक सम अफ द स्टुडेन्ट माइट बी इन्ट्रेस्टेड इन दिस एरिया एज वेल. सो मैले अलिकति त्यो पार्टलाई मात्रै जोइन मात्रै गर्न खोजेको यसमा है. अब यहाँनिर दुईटा किसिमको कुरा गरेको कारणले तपाईँ अलिकति हुनुभयो, कन्फ्युज हुनुभयो जस्तो. यो कम्पोजिट कोलम भनेको स्टडी चाहिँ थाइल्यान्डको लागि मात्रै भयो, नेपालको लागि गरेको होइन. त्यो चाहिँ रिकमेन्डेसन मात्रै भयो. त्यो मैले सेकेन्ड पार्टमा गरेको जोइन्टको इन्टेरियर जोइन्ट र एक्सटेरियर जोइन्टको पार्ट चाहिँ नेपालको सिस्मिसिटीको लागि भयो. त्यो भनेको चाहिँ तपाईँको एनबिसी 105 2020 को बेस्डमा डिजाइन गरेको कोलुम चाहिँ तपाईँको स्ट्रङ कोलुम विथ बिम बिहेभियर एक्जिबिट गर्यो भन्ने होइन. नर्मल डिप बिम होइन नर्मल डिप
So thank you, Dr. Bharat. So it's just a beautiful question. यहाँ अर्को एउटा क्वेसन आएको छ अनुज प्रधानले. उहाँले सोध्नु भएको छ, what was the strength of concrete used for precast concrete and cast in situ concrete in joint? What kind of admixtures were used in the concrete, if any? Sir.
थ्याङ्क यू अनुज फर द क्वेसन. अब यो कस्तो हुन्छ भने चाहिँ तपाईँको युज गर्दाखेरि प्रिकास्ट ओल्ड र न्यू कन्क्रिटको स्ट्रेन्थको युज गर्दाखेरि चाहिँ हामीले सकेसम्म चाहिँ सेम युज गर्ने कोसिस गर्छौँ, सिमिलर एफसी प्राइम युज गर्ने कोसिस गर्छौँ. अब अहिलेको युज गरेको केसमा जस्तो यो त पुरानो रिसर्चरको कुरा भयो है, त्यो कारणले गर्दा उहाँहरूले अलिक डिफ्रेन्ट युज गर्नुभएको थियो. अब जेनरली हामी चाहिँ के गर्छौँ भनेपछि सेम युज गर्ने कोसिस गर्छौँ. लेट मी फाइन्ड I don't know the exact value, so let me find. So this is the strength actually used by them. Let me see on my screen. So this is the strength of, so this is HPCC1, right? And this is HPCC2. कोरको केसमा चाहिँ सबैमा एउटै युज भएको छ. तपाईँको कोरको केसमा चाहिँ 40.1. हामीले के गर्छौँ भने जेनरली सकेसम्म चाहिँ प्रिकास्ट र कास्ट इन प्लेसको सिमिलर नेचरको हामीले युज गर्न ट्राई गर्छौँ है. अब त्यो एल सेपमा चाहिँ सिमिलर नै युज गरेको हो. तर अब यो रिसर्च अब पास्ट रिसर्चहरूको कुरा भयो है. HPCC1 को केसमा र HPCC2 अथवा मोनोलिथिक सबैको केसमा 40.1 भयो. अब प्रिकास्ट इन्केसमेन्टको केसमा चाहिँ फरक छ है. तब HPCC2 को केसमा 37.7 छ. अब सिमिलरली प्यानल 1, प्यानल 2, प्यानल 3, प्यानल 4 को केसमा फरक पर्छ. Please refer to this publication. You can refer detail. यसमा हेर्न सक्नुहुन्छ.
Any other questions from the floor? Okay, sir.
Thank you, Satish, for your nice presentation. And work also very nice and good work. So this column is hollow column. It is quite understood. But in case of wide beam, is it like this, or it was fully prepared in the outside, and then those two beams were placed at the joint?
Okay,
how those wide beams were precasted and then placed inside? Please elaborate.
Okay, sir. So talking about wide composite precast wide beam U-beam columns, right? So we have actually these forms of precast component, right? So we have precast U-beams. I think it will be more clearer from the test specimen detail, I think. So this one. So here, let me elongate it a bit more. So here, यसमा हेर्न सक्नुहुन्छ सरले जस्तो यहाँनिर चाहिँ कस्तो छ भने चाहिँ यू शेप को एउटा प्रिकास्ट बीम भयो सर यो, अनि यतातिर पनि अर्को यू शेपको प्रिकास्ट बीम छ, दुईटा प्रिकास्ट बीम छ. अब यो बीचको जोइन्ट रिजन छ नि जुन सर यहाँनिर तल हेर्नुभयो भनेपछि यो जोइन्ट रिजनमा चाहिँ स्ट्रक्चरल इन्टिग्रिटी छ. जोइन्ट भनेको एकदमै इम्पोर्टेन्ट क्रुसियल कम्पोनेन्ट भयो. त्यो कारणले गर्दाखेरि चाहिँ जोइन्ट रिजनमा चाहिँ हामीले प्रिकास्ट ड्राई कन्क्रिट युज गरेनौँ, हामीले वेट कन्क्रिट युज गरेको छौँ. अनि त्यसपछि अब त यसको माथि यसमा चाहिँ ए शेपको ट्रस, स्पेसियल टाइपको ए शेपको ट्रसहरू राखेको छ. त्यसको अब्जेक्टिभ पनि इन्टरफेस स्ट्रेन्थ नै बढाउने हो खासमा. तपाईँको कास्ट इन प्लेस कन्क्रिट फिल फिल गरेपछि दुईटा बिचको इन्टरफेस स्ट्रेन्थ स्लिपेजलाई घटाउने त्यो पार्टमा ए सेपको ट्रसहरू यहाँनिर राखेको छ। अब यसमा बेसिकल्ली कम्पोनेन्टहरू हेर्नुभयो भनेपछि तलको प्रिकास्ट कोलुम भयो विच हैज द reinforcement which are extruded. You can see the reinforcement and reinforcement or extruded reinforcement, sir, and it will be connected with mechanical splices from the above precast column. And this is precast U-beam and another precast U-beam, just two precast U-beam, and maybe there is one image, this one. So I think this one will be more easier to explain. यसमा हेर्नु भने अझ क्लियरली देख्न सकिन्छ होला सर। जस्तो यसमा युबिम 1 भयो फर्स्टको अनि युबिम 2 यो फुल्ली जोइन हुने होइन। अझ यहाँनिर हेर्नुभयो भने चाहिँ यो कलर कोडमा युबिम 1 भयो युबिम 2 भयो अनि भित्रको यो जोइन्ट रिजन चाहिँ कास्टिङ प्लेस कन्क्रिट अनि तपाईको माथितिर पनि प्रिकास्ट yes there will provided of main reinforcement, transverse reinforcement, everything.
How those post tension cables were laid?
It's very important question, sir. It's very difficult, very much congestion of reinforcement. यसमा हेर्नुभयो भनेपछि यसमा एकदमै गाह्रो छ यो सिस्टममा। यसमा हामीले खासमा लिटरेचरले खासमा एसिया स्ट्यान्डर्डहरूले के भन्छ भनेपछि दे सजेस्ट टु युज closed shape of stirrup. So we actually have to use closed shape of stirrup, but due to the fact which you mentioned already earlier, it's very difficult because there is the provision of post tensioning, there is the provision of top reinforcement, top longitudinal main reinforcement, and also the transverse reinforcement. So for that scenario, we actually adopted the open tie. So it is not closed tie actually. So maybe this one. So this one, if you see closely, so this is open tie. So एउटा full उसमा सबै reinforcement tie गरेको छ. It is not a close. A close राखेको भए एकदमै गाह्रो. त्यो congestion reinforcement congestion को कारणले गर्दा हामीले open tie राखेर अनि त्यसपछि यसमा तपाईले मेन बार पनि भित्र छिरेको मेन बार देख्न सक्नुहुन्छ अनि माथिबाट तपाईको transverse reinforcement पनि देख्न सक्नुहुन्छ.
All right, so we'll take two more questions and then probably finish the Q&A session.
एउटै थियो हजुर हजुर एउटै नै थियो त्यो टेस्ट नै गरेको हुन्छ त्यो स्ट्रेन्थ चाहिँ कतिको फरक पर्छ भनेर टेस्ट नै गरेको हुन्छ.
All right, तपाईले के सोध्नु खोज्नुहुन्छ?
सर यो केसमा चाहिँ इन्केसमेन्टको कुरा भयो त्यो इन्केसमेन्टले चाहिँ कन्फाइनिङ एक्सन दिएको थियो कि छैन हामीले त्यो कन्सिडर गर्नुपर्ने.
You are talking about L-shaped precast plate, right? So talking about L-shaped precast plate, let me explain. अब यसमा कस्तो छ भनेपछि कन्ट्रोल कोलुममा हेर्नुभयो भनेपछि त्यहाँनिर कन्फाइनमेन्टको इफेक्ट चाहिँ थिएन है. जस्तो यहाँनिर डिलामिनेसन, यु क्यान अभियसली सी द डिलामिनेसन, राइट, डिलामिनेसन अफ प्रिकास्ट इन्केसमेन्ट. बट टकिङ अबाउट द मोडिफिकेसन वी कुड सी द कन्फाइनमेन्ट, बेटर कन्फाइनमेन्ट. एक्चुअली मैले सबै रिजल्टहरू चाहिँ देखाएको छैन. अब यो चेक गर्न मिल्छ तपाईँको जस्तो स्लिप कति भयो, डिलामिनेसन कति भयो, तपाईँको स्ट्रेन्थ त्यो एक्सिड भएको छ कि छैन, अब कति पछि चाहिँ डिलामिनेसन हुनसक्छ, कति ड्रिफ्टमा डिलामिनेसन हुन्छ भन्ने त्यो सबै कुराहरू हेर्न मिल्छ. आइएम सरी टु से आई हेभ नट केप्ट दोज अल इन्फर्मेसन इन दिस स्लाइड. सो टकिङ अबाउट योर क्वेसन, देयर वाज कन्फाइनमेन्ट इफेक्ट.
Alright, there is one more.
हामीले त्यो कन्फाइन लाइक के मोडल र म्याथमेटिकल मोडलहरु के
I could not get your question. Confinementले इन्क्रिज गर्ने भनेको शियर स्ट्रेन्थ हो अनि त्यसलाई I couldn't.
Google Meet, Sabin Raut has raised a question, and probably he was trying to ask whether these structural systems have been used in real life situation. Of course, you have actually inferred from the real life situation.
Yes.
And what is more, how much was the cost saving in construction adopting this method compared to its counterpart?
I cannot say the exact figure, right? It's not like percentage, right? 30% saving, but it was saved, like I already mentioned, right? So actually, cost of homework is far more. Like it actually incorporates around 30 to 40%. And in some cases, almost up to 60% also. So using this kind of system, it obviously save the cost. So thank you very much for your question.
Thank you, Dr. Saab. All right, everybody, thank you so much. It was such a vibrant lecture. The first, albeit the fact that this is our first lecture of the CNEP lecture series. Once again, thank you so much. हाम्रो आजको यो lectureको official sort of जुन छ program त्यो सकिएको छ, तर would like to take some views from Motra sir, if you like to have a few sentences overall on the proposed CNEP lecture series and on this particular lecture. And after that, we'll have a concluding remarks from our president, Rajan sir, and then we finish off. After that, we will have a small tea session, which is basically a networking session, but 2 to 4 would be the networking session. We can just mingle with each other, and then from 4 to 4:45 we'll have a dedicated lecture series where you will have to keep everything silent, and then from 4:45 to 5 we'll have question answer session, some sort of remarks like this. So over to Motra sir, हजुरले आफ्नो थोरै वक्तव्य राखेर जानु होला, त्यसपछि राजन सरले आजको यो लेक्चर सिरिजमा कन्क्लुडिङ रिमार्क्स दिएर लेक्चर सिरिज अफिसियली सकिएको पनि अनुरोध गर्नको लागि म अनुरोध गर्दछु. Once again, I am Shankar Dhaka, working as the General Secretary of CNEP 9th Executive Committee. Thank you.
Thank you, Shankar sir, for your kind word. Chair of the session, all the members of CNEP, as well as all structural colleagues, structural engineer colleagues. First of all, I would like to congratulate CNEP organizing such type of very nice and useful talk series on the structural engineering, and giving me a chance to talk about this. I would like to thank and congratulate Dr. Satish Paudel for his work and his presentation, today's presentation. From his work, we can see that how he was very dedicated student and how he worked in his PhD research. Everything can be seen in his presentation, and this work, if we can apply his research in our condition, it may be wonderful. I think whatever it told regarding the cost of homework is very much high, and in our case homework is very poor due to the lack in quality control of homework. We structural engineers are not able to achieve the desired quality of the concrete. It is fact in our case. So if we are able to apply those kind of system, we can improve, we can expedite the construction time as well as quality also. But Dr. Satish already mentioned that there are some constraints and difficulties also. Our country lies in a very active seismic region, and we should be very careful